In statistics, quality assurance, and survey methodology, sampling is concerned with the selection of a subset of individuals from within a statistical population to estimate characteristics of the whole population. Each observation measures one or more properties of observable bodies distinguished as independent objects or individuals. In survey sampling, weights can be applied to the data to adjust for the sample design, particularly stratified sampling. Results from probability theory and statistical theory are employed to guide practice. In business and medical research, sampling is widely used for gathering information about a population. The sampling process comprises several stages: defining the population of concern, specifying a sampling frame, a set of items or events possible to measure, specifying a sampling method for selecting items or events from the frame, determining the sample size, implementing the sampling plan, sampling and data collecting, data which can be selected, population definition. Successful statistical practice is based on focused problem definition. In sampling, this includes defining the population from which our sample is drawn. A population can be defined as including all people or items with the characteristic one wishes to understand. Because there is very rarely enough time or money to gather information from everyone or everything in a population, the goal becomes finding a representative sample of that population. Sometimes what defines a population is obvious. For example, a manufacturer needs to decide whether a batch of material from production is of high enough quality to be released to the customer, or should be sentenced for scrap or rework due to poor quality. In this case, the batch is the population. Although the population of interest often consists of physical objects, sometimes we need to sample over time, space, or some combination of these dimensions. For instance, an investigation of supermarket staffing could examine checkout line length at various times, or a study on endangered penguins might aim to understand their usage of various hunting grounds over time. For the time dimension, the focus may be on periods or discrete occasions. In other cases, our population may be even less tangible. For example, Joseph Jagger studied the behavior of roulette wheels at a casino in Monte Carlo, and used this to identify a biased wheel. In this case, the population Jagger wanted to investigate was the overall behavior of the wheel, while his sample was formed from observed results from that wheel. Similar considerations arise when taking repeated measurements of some physical characteristic such as the electrical conductivity of copper. This situation often arises when we seek knowledge about the cause system of which the observed population is an outcome. In such cases, sampling theory may treat the observed population as a sample from a larger superpopulation. For example, a researcher might study the success rate of a new quit smoking program on a test group of 100 patients, in order to predict the effects of the program if it were made available nationwide. Here the superpopulation is everybody in the country, given access to this treatment, a group which does not yet exist, since the program isn't yet available to all. Note also that the population from which the sample is drawn may not be the same as the population about which we actually want information. Often there is large but not complete overlap between these two groups due to frame issues, etc. Sometimes they may be entirely separate. For instance, we might study rats in order to get a better understanding of human health, or we might study records from people born in 2008 in order to make predictions about people born in 2009. Time spent in making the sampled population and population of concern precise is often well spent, because it raises many issues, ambiguities and questions that would otherwise have been overlooked at this stage. Sampling frame. In the most straightforward case, such as the sentencing of a batch of material from production, it is possible to identify and measure every single item in the population and to include any one of them in our sample. However, in the more general case this is not possible. There is no way to identify all rats in the set of all rats. Where voting is not compulsory, there is no way to identify which people will actually vote at a forthcoming election. These imprecise populations are not amenable to sampling in any of the ways below and to which we could apply statistical theory. As a remedy, we seek a sampling frame which has the property that we can identify every single element and include any in our sample. The most straightforward type of frame is a list of elements of the population with appropriate contact information. For example, in an opinion poll, possible sampling frames include an electoral register and a telephone directory. Probability and non-probability sampling. Probability sampling. A probability sample is a sample in which every unit in the population has a chance of being selected in the sample, and this probability can be accurately determined. The combination of these traits makes it possible to produce unbiased estimates of population totals by weighting sampled units according to their probability of selection. Example: we want to estimate the total income of adults living in a given street. We visit each household in that street, identify all adults living there, and randomly select one adult from each household. We then interview the selected person and find their income. People living on their own are certain to be selected, so we simply add their income to our estimate of the total. But a person living in a household of 2 adults has only a 1 in 2 chance of selection. To reflect this, when we come to such a household, we would count the selected person's income twice towards the total. In the above example, not everybody has the same probability of selection. What makes it a probability sample is the fact that each person's probability is known. When every element in the population does have the same probability of selection, this is known as an equal probability of selection design. Such designs are also referred to as self-weighting, because all sampled units are given the same weight. Probability sampling includes simple random sampling, systematic sampling, stratified sampling, probability proportional to size sampling, and cluster or multi-stage sampling. These various ways of probability sampling have 2 things in common. Every element has a known non-zero probability of being sampled and involves random selection at some point. Non-probability sampling. Non-probability sampling is any sampling method where some elements of the population have no chance of selection, or where the probability of selection can't be accurately determined. It involves the selection of elements based on assumptions regarding the population of interest, which forms the criteria for selection. Hence, because the selection of elements is non-random, non-probability sampling does not allow the estimation of sampling errors. These conditions give rise to exclusion bias, placing limits on how much information a sample can provide about the population. Information about the relationship between sample and population is limited, making it difficult to extrapolate from the sample to the population. Example: we visit every household in a given street, and interview the first person to answer the door. In any household with more than 1 occupant, this is a non-probability sample, because some people are more likely to answer the door and it's not practical to calculate these probabilities. Non-probability sampling methods include of convenience sampling, quota sampling and purpose of sampling. In addition, non-response effects may turn any probability design into a non-probability design if the characteristics of non-response are not well understood. Since non-response effectively modifies each element's probability of being sampled,